All right, so our talk's going to be about hacking like in the movies. You know, when you're sitting down and you see that person logging into terminal and everything's kind of shooting by, there's colors, there's 3D animations, and you think, I wish hacking was that way. So we actually try to do some visualization of page tables, like in the movies, with fancy graphics, not so fancy at the end though, and try to see if we get any interesting results out of that. So I'm supposed to be Alex Radocea. He was supposed to give this talk. He's Romanian. He worked at Apple. He works at CrowdStrike. He's in San Francisco. I'm Romanian. I worked at Apple. I work at CrowdStrike. I'm in San Francisco. So they thought I'd be a good replacement. So I'm not actually Alex Radocea. I'm actually Alex Ionescu. Close enough, I guess. So I used to work on ReactOS for a long while, which is a project that tries to re-implement Windows NT from the ground up. So there are a lot of Windows internals. You may have read the Windows internals books. They're big, bulky, and heavy. Co-authored those with Mark and David, doing a bunch of courses. Ironically, what do you do when you reverse Windows your entire life? You go work at Apple. So I did that for a few years, worked on the kernel of iOS and OS X, and then I moved on to CrowdStrike, where I'm currently chief architect. I'm here with Georg.
All right. I'm Georg. So I was announced as Georg, and I am actually Georg. Alex could be here, but we've got another Alex, right? That's good enough. I work at CrowdStrike too. I'm a researcher there, and yeah, I do pretty much like all low-level stuff, x86, ARM, reverse engineering, and binary fun stuff like binary exploitation. But mostly malware analysis. If I exploit stuff, then it's to learn the techniques of the evil guys and to develop mitigations against those. Yeah, that's my Twitter and blog, but yeah, that's really it. So I'll give it back to Alex to actually do the intro.
Thank you. So, quick little intro. Paging is basically the mechanism through which modern processors can give you a virtual address that maps to a physical address. We don't want things touching physical memory. We want to have protection. We want to have sharing. We want to page things out to disk. So most processors implement what's called an MMU, which lets you translate a virtual address, which is specific to a process and can have certain permissions, into a physical address that's on your machine that actually corresponds to a memory cell on RAM. So you probably already know that. Now, most implementations try to pick a page size, some unit of allocation that makes sense. What chunk of virtual memory should be translated to how much physical memory? That can be 4 kilobytes, 8 kilobytes, 2 megs, depending on what's called the page size. Most CPUs also implement translation look-aside buffer, so once we've done a translation from physical to virtual, from virtual to physical, we don't have to keep doing it again and again and again. Now we're going to be talking about 3 different architectures. We're going to be talking about ARM, x86, and x64. Most of what we've done is only on ARM and x64, but I'll mention a little bit about x86 desk paging as well. In all these architectures, you have a nested or hierarchical system that lets you translate a virtual address to physical address. And this is basically based on different levels of translation. So after this translation is done, or during the translation, we also have protection that can be applied. Things that say, for example, this page, this kilobyte, or this 4 kilobyte is read-only, or read-write, or executable, or read-write executable. And also we can say if user mode can access it, so if applications can touch it, or if kernel mode can access it, if supervisor level applications, drivers, and so on can affect it. And then there's additional technologies that have been added on, just like SMEP, PXN, you can Google all these terms. Basically, processors trying to be smarter and smarter about protecting access to regions of memory. So, just to give you a quick little intro for those of you who are not too familiar how paging works. On the top here, we've got a virtual address that's going to be, let's say, 32 bits on 32-bit x86. What happens is you break up this address into different selectors. And the processor has a register called CR3. CR3 is a physical address that the OS programmed into the processor. And this corresponds to what's called a page directory. This will represent all the virtual addresses in that process. So CR3 tells us tells the CPU where the page directory is. Inside that page directory, we've got 1,024 entries. The first bits in the virtual address tell us which one of those 1,024 entries we're going to pick up, and that entry points us to another table. Now we go to the second level, which is called the page table. Now that we have a page table, it also has 1,024 entries, and we know which one to pick by taking the next bits in the virtual address. Now we know which page table entry to look at, which points us to a 4 kilobyte page. Now we have the 4 kilobyte in memory, and the last 12 bits in the address tell us which byte in that 4 kilobyte region should we access. And other than this, of course, we also have the permissions that are going to be mapped in there. So that's how we can go from 0x something something to an actual page in memory. And we also have what are called large pages. If you think about it, you have 20 megabytes of data that are all read-write. And as you're scanning through this 20 megabytes, you're constantly doing this conversion. Well, if you're going to have a large piece of memory that has the same permission, you can set up what's called a large page. And a large page is an entry in a page directory that directly points to physical memory. And how much physical memory does it point to? Well, if you think about it, a page table has 1,024 entries. Each entry describes 4 kilobytes, so a page table describes 4 megs. So then a large page describes 4 megs directly without having to break it up in little chunks. Now, if a page entry here describes 4 megabytes and I've got 1,024 here, that means a page directory describes 4 gigs, which makes sense because we're talking about x86 and 32 bits. So 4 gigs of address space, which is what we have, is described by one page directory. Now, Intel also developed what's called PAE, Physical Address Extension. With PAE, you can address more physical memory because there's more bits for physical memory, and you can have a bit that's marked as non-executable. So now you can have pages that are executable or non-executable. In the original system, they never thought of this. They said read, write, that's all we care about. Execute shouldn't mean anything. Now we know that's different. The interesting thing that happens there is to add that one extra bit, they have to make all these entries bigger. And you can't just add an entry, 1 bit, because this is a 32-bit structure. You don't want to have a 33-bit structure. That's kind of weird. So they made these 64 bits. Well, now a page table can't fit 1,024 entries. If there's 64 bits, it can only fit 512 entries. And so now a page table only describes 2 megs. So a page directory would now only have 1,024 entries describing 2 megs each, so it would only describe 2 gigs. But the page directory entries themselves are also 64-bit now, so I've only got 512 entries. In other words, a page directory on PAE, when you have no execute support turned on, only describes 1 gig. So you actually have another level further up, which now describes which page directory you want to use, and each entry describes 1 gig. And I mentioned that because as you go on 64-bit, that just keeps going on further and further. Now on 64-bit, we have those 1 gigs that are described with 512 entries, which gives us 512 gigs. We have a 64-bit address space. That's not enough. So we have another directory which describes terabytes of memory and so on and so forth. In fact, this is starting to get so complicated that AMD gave up. So we don't want to do 64 bits. So they capped it at 48. Even the most modern 64-bit processor only uses 48 bits of address space because they didn't want to implement the other levels. It's getting just too messy. Maybe one day they will. So what we did for this talk is we basically visualize these structures, and Georg is going to talk more about that, in terms of finding out what are all the mappings and what are the permissions behind those mappings. So I'll let Georg take over.
All right. So as you can see, Alex is a technical guy, right? He knows a lot of very technical stuff, and yeah, the idea is right. You know, we have this complicated stuff. We turn it into very, very pretty pictures that we can look at and then understand it. So what does a hacker from a movie actually look for, right? I mean, in the movie, you just see them looking at these pretty pictures, but what are they looking for in those pictures? So if they are visualizing page tables, they're probably looking for mappings that have constant addresses. So you take the picture not only once, but you take a couple of these pictures and you compare them, right? And if the same things appear at the same place in these pictures all the time, that means they're always at the same address. And that means basically when they're always at the same virtual address, that is an ASLR bypass because this piece of memory is actually not being randomized. It's at a static fixed location. If it is a constant physical address, it means it's always on the same, physical chip in the RAM. And that can be interesting, for example, if you do some stuff like Firewire or Thunderbolt attacks, like, these DMA attacks where you capture the physical memory, if you can, because those work on physical addresses, so it's interesting to be able to predict physical addresses. And most ASLR and operating systems these days, they randomize the virtual addresses, but as Alex will actually show later, there's some stuff that's sometimes on some architectures always at the same physical location. And then also, besides comparing pictures and looking for stuff that's at the same place, we also look at the actual fancy colors things have, and these colors describe the actual protections. So if there is mappings that have unexpected protections, that could be very interesting as well. For example, if there's a mapping that is readable, writable, and executable. That means I don't actually need to do return-oriented programming, right? I can take my shellcode, put it in the mapping, and jump right there, and do the casual knob slide thing from the 90s. And yeah, then we're also looking at DMA memory and what drivers are actually doing, because one of the things why we actually visualized the page tables and didn't just ask the operating system, hey, what memory is mapped how, is that drivers sometimes, depending on how they implement it, they don't tell the operating system we're allocating this memory here. They just reserve it directly from the DMA engine, for example, and then you get actually different results asking the operating system or visualizing directly the data. So we did a lot of data collection of these page tables. Every time we wrote some, custom hacky code, so that's why there's not, no awesome tool that we can release because it's architecture specific. And we collected the data directly, as I just said, from the hardware. So we, didn't ask the operating system. So on Android, what we did to collect the data is that I both tried building a custom kernel. So for the flagship devices that Google supports, it's fairly easy to get a working source for the kernel and build a working kernel yourself. And we use the modified kernel to collect this data from the hardware directly, because you need to have the right privileges to talk to the hardware in this way, right? And also what we did for a couple of other devices is that we weaponized a local exploit to actually collect this data in the kernel shellcode. Because for some of the devices, the vendors give you this in the spirit of the GPL, they give you a tarball of the source, but it's next to impossible to actually build the source and deploy it on the device, right? It's to comply with the license, not for actually building your own kernel. For iOS, Alexandru, who's not here, wrote a custom driver for a jailbroken device. So he took an iPhone, took a public jailbreak, and then wrote a custom driver to collect this data from the kernel directly. On x64 Linux, we did a custom kernel module. On x64 OS X, we also did a custom kernel extension to collect this data. And for the Windows architectures, actually, Alex worked with crash dumps. So, and for 64-bit, did you actually use the custom driver?
At some point, you get physical RAM.
Yeah, the physical stuff, right. So the crash dumps and a custom driver there. So as you can see, we did a lot of driver development, kernel code writing, and so on. And that's how we grabbed all the data. So how did we visualize it? We used Hilbert curves. So what's a Hilbert curve? A Hilbert curve is a so-called space filling curve. And you might be actually very familiar with them from visualizing the internet address space, right? So what a Hilbert curve, and I'll show you some so it's easier to understand, is basically just a visualization of the whole address space in one picture. And instead of, as other people, for example, use it to visualize IP address space, we use that to visualize the memory address space. And we actually used public implementation from a guy called Aldo Cortesi. That's his website, and we adapted his S-curve, which is space curves, and used his Hilbert curve code. We adapted that to actually visualize the memory, and had some simple data parsing to parse the data output from our data collection tools. So that's the basic methodology. So I'm going to introduce a legend here in one slide. So I'm always referencing this. What you're probably interested in is the RWX protection that you see there, right? So that is, that's this one here, and this one here. So basically pink and strong blue are the interesting one, because if something is writable and executable, as I said, you can just drop your shellcode there and jump to it, right? You don't need to do return-oriented programming. So those bright colors are probably interesting. What's also interesting is stuff in the kernel that's read and writable, right? Because the kernel is really interesting attack target, and if something is readable and writable, you can place your data in the kernel, which is interesting if there's other stuff readable and writable that is not only just the heap, something like this, right? So this is the general colors, and the least interesting here probably is user read only. Well, you can only read the data and it's in user space. Yeah. So that's just a general methodology. The really interesting stuff is looking at the pretty pictures, right? I mean, that's what everybody's here for the pretty pictures, and that's what movie hackers do as well. They look at pictures. So the first set of case studies now for the Android operating system, I guess everybody knows what that is. And then Alex is going to take some more case studies later. So the first thing, as I said, is of course take a couple of pictures and compare them with each other. So what you see here is what I just talked about. This is the Hilbert curve, right? So let me explain it a little bit more. What you see here is add receiver, right? And this is actually the init process on the phone, so there's not much to see here. There's almost nothing here in user space. And recall that Android is actually a Linux, right? So on Linux, you have a 3 gigabyte, 1 gigabyte split. So the lower 3 gigabyte are reserved for user space, and the upper gigabyte is where the actual kernel is, and that's talking virtual memory addresses. So what you see here, there's almost nothing in user space. There's like, some mappings here, but yeah, that's not. Well. Aha. So you see there's like some small mappings here. So these pixels there, can you actually even see them? Right. So there's some stuff there, but as I said, right, and there's like a little bit stuff here, but that's really it. Like there's not really much to see. And this is actually from the collection program, or not actually from the init program. You can see already this is blue. There's something that's writable and executable, right? But nobody's going to attack init, so it doesn't really matter. And the thing that is almost fully populated is the kernel space, because it doesn't matter which process you're looking at, the kernel always is the same, the memory space, and you see all the kernel stuff in there. So let's compare this with a fancy animation to another process. This is now DHCPD, right? This is also running on the phone, so it's issuing DHCP requests. You see there's a little bit more stuff up here, right? There's some more allocations here, some stuff, and yeah, notice again how this is blue, right? Writable and executable. But yeah, some mappings that are read-only, some are read-only, execute-only. So it's a little bit mixed there. Which is already interesting because DHCP is a network daemon, all right? Why is some stuff writable and executable there? So let's compare this further. This is actually a zygote. And the zygote on Android is a process, it's like kind of the mothership process for all the Java processes. So every time you spin up a new app, you open a new app, it's actually forked off the zygote process. And that has an interesting effect, because if you now compare these mappings here, if I go to the next one, which is my email, that's actually my actual phone. If you compare these two, you see that a lot of stuff is staying in the same place, right? It's generally not so well randomized. It's not spread all over the place. If you compare these two, there's a lot of stuff here in that region here that's staying at the same place, right? And that's a known problem actually for Android. Android has user space ASLR, and they randomize almost everything, but it's always at the same addresses during one boot for the Java apps, because they all fork from zygote. And if you're familiar with Linux, fork means that they retain the same virtual address space for efficiency, right? It saves you some memory, but it's all in the same space, right? So that's an interesting finding for a movie hacker. We have ASLR, but if we're running in one process that is forked from zygote, we actually know the exact addresses that stuff will have in another process. All right. And then there's another interesting finding here. Whoops. Which is actually, I was getting my own legend wrong. The blue stuff is read execute. The pink stuff is the interesting stuff, right? So the interesting stuff is that here you see actually some Java JIT going on, right? And that's another finding. The JIT stuff that Dalvik is doing is writable and executable. So if you can predict the address of the JIT in one process, you can just place your shellcode there and dump there. And now if you compare this further to sandbox process 0, which actually belongs to Chrome. So Chrome has a sandbox on Android, which is not really a sandbox. It simply drops a UID. And that also forks from the Chrome process, and the Chrome process is actually Java process forked from zygote. So even Chrome has some stuff in the same areas here again. And you see the kernel stuff is always the same. It's always at the same addresses. I mean, some of the kernel mappings change a little bit if you look there in the left there, but that's just because it's not exactly at the same time. All right. So that's generally comparing Android processes, and the first finding there is ASLR on one single device, as it is known for zygote, or due to zygote does not really work. Okay, let's look at a Galaxy Nexus capture now. And this is actually, the user line process is not interesting, but what is interesting about this here is the kernel. This is from another device, right? And if you compare these two here, you see that, for example, here there's some stuff that's actually not writable, right? If you now go to this other device, the Galaxy Nexus device, you suddenly see there's a huge section here that's writable and executable, right? The section down here is writable and executable, and that's the kernel text segment. So what does that mean? That means basically if you do a local attack against the kernel, right, for example to do a jailbreak or to just escape the sandbox from Chrome, anything to get root on the local phone, it's not really hard because the entire text segment on this specific device, the Galaxy Nexus, will be writable and executable. And actually, if you look at GeoHot's active S4 exploits, that's actually what he did. He used a bug that is very hard to normally use, which is basically the primitive that you gain from the bug is incrementing a single address. And what he did is he directly incremented code itself. So he changed an instruction by incrementing its representation in memory. And that was only possible because the kernel memory is writable and executable. So if you compare this with another device now, the Nexus 7 has the same issue. And there's a lot of more writable and executable code here, right? All of this is writable and executable. So Nexus 7 is a Tegra device, right? NVIDIA Tegra is a specific chipset. And the Galaxy Nexus is a Samsung device with a Samsung chipset in there. Now, if you compare these devices now to the Galaxy S4, which is running Android 4.2.2 on an MSM chipset, you will see now that actually it's a little bit better there because you have a little bit of code here that is read-only execute. And I mean, there's all these writable, executable pages all here. You can still drop your shellcode there and jump there. But the actual kernel code, this here, down here, is the actual kernel code. This cannot be written directly to. So they have the MSM kernel has a little bit better security than the other kernels. And that's really an interesting finding because why does a specific chipset have other protections than other kernels, right? Why is it harder to own a Qualcomm chipset on a device than own, say, NVIDIA Tegra chipset? That's very simple to answer though. And one thing I forgot. There's one thing that's really hard to see, but and to overlook and forget, but Android hackers have, zooming capabilities. There's something here. You see the blue pixel there, right? And the sort of blue pixel below, it's actually an artifact from an image compression, so ignore that. So you see the one blue pixel there, right? Okay, so that is actually on the Nexus 7, the Tegra device. And then let's look at the Galaxy S4, right? Again, there's this blue, and giant crosshair, and a blue pixel there, right? And let's go back to one of the userland stuff we did. And let's zoom in on that. Somehow. I'm not really familiar with Alex's awesome zooming tool. Okay, there's a blue pixel there, right? And what did I say earlier? We compare pictures, and there's a blue pixel that is always at the same location. So what does this blue mean? You all recall from the legend, the blue stuff is userland read execute, right? So what does that mean? We have a userland read execute mapping that is always at the same position. Well, that might be interesting, right? But what's more interesting is that, as I said earlier, this gigabyte here is the kernel space. But there's a page in here that's user executable deep inside the kernel address range. That's kind of weird, right? So I looked into that after spotting this blue pixel there. It's a little bit easier if you have a bigger screen, right? So what's Android observations? We have this fixed read execute mapping at this one address. So just believe me that this one blue pixel is at this specific address there, FFFF000, and it's always at the same location, and it's readable and executable by user space. So what is this page normally, right? You look into the architecture manuals to understand what is this magic address, right? It looks kind of magic already. So if you read that up, it's actually the ARM exception vector-based address. So on the ARM architecture, it's like a processor, and the processors have interrupts. And interrupts are triggered by hardware events, for example. Interrupts are triggered, software interrupts are triggered by the normal user space program to issue a system call to the kernel. And every time there's an interrupt on the ARM architecture, it goes to this vector page table and to look up the handler address for this interrupt, right? So why is that executable for the user space though? Because this is stuff that runs, and interrupt handling is an operating system task, and user space doesn't need to execute there. Well, the kernel developers of Linux thought ARM is an embedded architecture, right? So let's save some memory and cram all we can, all we need that needs to be executable for the user space in the same page. So what they did is basically they took some helper code that is accessible per the ABI, per definition to user space, and put it in the same page. And because they put it in the same page, and it's code that is supposed to be called by user space, the page must be executable by user space. Well, but long story short, what is this? This is an ASLR bypass for Android because you have always code that you can predict the address for. And then, as I said earlier, the kernel text section is writable and executable on almost all kernels. There is a kernel configuration setting that's called like config_debug_read-only data, but it's not set in the actual vendor configurations, right? When you get a vendor kernel on the phone because you just bought the phone and don't flash a custom kernel like I think 99% of the population, then this is not set. So you have a writable and executable kernel. The only exception was this 3.4 MSM kernel, which has a read-only text section. And that's actually because Qualcomm did a really good job, so I want to call them out for being awesome. They have a custom kernel patch which adds a config setting that says config strict memory RWX, which was written by Qualcomm engineers, and that is why the Qualcomm kernels have non-writable text, non-writable kernel code. They kind of overlooked 2 megabytes that are still writable and executable though. Do you see them here in this picture? Right, this is, all right. This is writable and executable here, right? You see that these two blobs there are 1 megabyte each. And again, they have a fixed address, right? This right down there, this is address C0000 and so on. It's where the kernel actually starts. And that's writable and executable again. So again, on Qualcomm kernels, you can just drop your shellcode in there, write it and execute it directly. So you don't need to do any return-oriented programming in the kernel, even on Qualcomm. But you cannot directly modify the original code. Okay. So I introduced all these findings. Now, how do we actually practically bypass ASLR on Android? When I wrote these slides, I looked at Android 4.2.2. I briefly verified that it's still the case for 4.3. So this is really like latest Android version ASLR bypass. So there's a couple of interesting gadgets that they put in this page that are used for helping the user space. There's one gadget that is called kuser compare exchange, and it always has this one very specific address there. And what it basically does is if and only if the value pointed to by register 2 is the same as the value contained in register 0, then it actually assigns to this memory location the value of R1. Or in other words, you give it 2 registers that contains values and 1 pointer, and if the value at the pointer is the one that you gifted first, that's the compare part, it actually exchanges this to the other value you gave it, right? It's useful if you do like atomic, unlocked walking off linked list in a thread safe manner, for example. So one of the uses for this gadget would be, for example, if you can invoke a code like you say you have a vtable pointer overwrite bug, if you can invoke this code and control these registers, which is very, very common because these are the first 3 parameters passed to a function, then you can repeatedly invoke this and brute force the address of a function. And without having any info leak, you can create an info leak in this way from code execution. Or because it's at a fixed address and this is composed of multiple instructions, this gadget, you can just jump past the equality check, past the compare part, and actually just use what's called the exchange part and turn this into an arbitrary write gadget, which is again useful if you want to write to stuff. And there's another gadget that does exactly the same thing for 64-bit values. So it actually compares 2 machine words and also has a fixed location. And there's another interesting piece in there, and that is the actual interrupt handler for the software interrupt, which is depicted here, which loads the value to branch to. So this is a bit of ARM assembly, right? It says load into the PC, the program counter register, the value at program counter register plus something. So it dereferences another address, which is here on the right. Oh, yeah. You can see if I'm pointing with my hand on my own screen. So this is the actual address it's loading the value from. As you can see, this is still on the same page, so we can load this value. And this is the destination address this is jumping to. What does that mean? It means this is a kernel information leak. And it leaks the actual code address of the system call handler. So if we are using a local attacker who wants to do a jailbreak, who wants to elevate to root, and we don't have information about the kernel, we can get actually the address of the system call handler from this information leak. And in combination with the information we have before, that on many kernels and many devices, the actual kernel is writable as well, we can now get the address of the system call handler, and we can directly write to it. So we can actually modify the code of the system call handler to do, whatever, give us a root. Okay, so that's actually the ASLR bypass. And because we're good guys, we try to responsibly disclose this. Because ARM Linux mostly affects Android these days. I mean, other people use Linux on ARM, but 99% of the Linux installations on ARM are really Android. We talked to Google, who put us in touch with a couple of people, and there was a very, very quick patch from Russell King from ARM, who I want to call out. Nice job. I reported this, and 3 days later he came with an actual kernel patch, which adds some intra-page randomization. Very nice idea. The problem is that this is only a partial solution because the user space helpers still need to have this fixed address because of backward compatibility, right? If you look at Bionic, the libc on Android, it actually relies on this hard-coded address. So, the actual user land on Android kind of relies on this ASLR bypass with this fixed code location in their own code. And it also modified the vector handlers to branch into an adjacent page so that you can actually, that is not map readable to user space anymore, so you cannot leak kernel addresses that way at least. And then instead of being filled with knobs as it is right now, the page is actually filled with undefined instructions which will generate an exception if you branch to them. So you cannot if you just randomize it right now, when it's filled with knobs, you just jump into kind of what is a knob sled placed there by the operating system. But with that nice modification, you can actually generate an exception. And it's really nice. It took only 3 days, and I was like, wow, they patch stuff fast, shit. But actually, it's still not patched. Why is it not patched? Why is the patch not available? Well, I mean, even if it was available, it probably would take years until you really find it on a device, because that's Android, right? But even they didn't make the patch available yet because they used the entropy, the random number generator in the kernel, to do the randomization of the addresses. And if you boot a phone, it doesn't have any sources of entropy to seed the random number generator. So what that means is that if you turn on the phone, it always is at the same random location. So, I mean, the location isn't static anymore, but the random number is always the same. So the patch is awesome, but kind of ineffective. And so there's now a huge back and forth between security at kernel.org and this ARM developer, which was, really fun. And hopefully this patch will make it soon. Is there a direct remark to that?
Yeah, I was just thinking, shouldn't or doesn't all Linux distributions save entropy when you shut down or?
Yeah, generally yes, but the whole discussion now that goes on this mailing list is basically, this is an early init call, and this is a late init call, and it's all about init calls, and at that point you can't read the block devices yet. So the vector page is being randomized so early in the boot process that the saved entropy is not available. So there was some ideas, we should save some entropy in the bootloader to pass as a boot argument, and all fancy ideas, but in the end it was a very amusing back and forth for 1 month between kernel people saying each other like, yeah, we suck at security, and we need to be more effective. All right, that's my little bashing on Linux, and yeah. Alex,
thank you. All right, so the next case study, Alex did with some dumps, is a Surface RT. So we'll actually talk about Surface RT now, and then Windows 8 64-bit. So some of the stuff we're going to see here is going to be 32-bit and ARM, and then we're going to go to x64. So some of the issues here are going to be ARM specific, some of the other issues are going to be 32-bit specific. So starting with Vista, Windows has what's called a kernel virtual address space allocator that basically picks a available location using a random allocator every time anyone in the kernel needs some memory. So if you want some heap, you want some stack, you want to load a driver, there is no fixed address like there used to be in XP. In XP, in Windows internals, we had 2 pages that told you every single address and what was going to be there on every machine in the world, which was nice for hackers. So in Vista later, it's all kind of randomized by virtue that there's an allocator that always picks a page. So it's quite fragmented. Now, however, the issue was that even though the locations were getting randomized, they were all read, write, and execute. And so you had these large chunks where, yes, I might not know what's in that chunk, but I know it's read, write, execute, and that could be useful already. In Windows 8, they did a lot of work to not only randomize these regions on 32-bit, but also to make sure that they're not read, write, execute, because there's no reason for them to be read, write, execute, in many cases. This is a slide I borrowed from Matt Mueller's presentation at BlackHat, I think last year, if not 2 years ago, I think last year, about the changes they had done in Windows 8 regarding this issue. And if you see here, on 64-bit, Windows 7, all of this was executable, and it all became non-executable. The other thing they did in Windows 8 was to add this non-paged pool that's also non-executable, so they added a separate subtype, and that's non-executable. And then on ARM, the default, so executable non-page pool still exists, but the default is non-executable non-page pool. On x64, drivers have to opt in for it though, but still the end result of this was that almost everything, well, everything except what was supposed to be executable on Windows 8 is non-executable. But we'll see there's actually some small piece here that was actually missed, and there are things that are supposed to be executable, and are they static? So that's what I try to look for. Number one, were there things that this missed? Were there things that were still executable? And number two, what are the things that are supposed to be executable but are not getting ASLR properly? So we either have an ASLR failure or we have a failure to mark a region non-executable when it doesn't need to be. So Surface RT runs the Windows 8 32-bit kernel. Very locked down though compared to a regular 32-bit kernel. So you're not allowed running anything else but Microsoft signed binaries or store applications, which also have to be signed, and they run in a sandbox. So you can only run sandbox apps or Microsoft apps or Microsoft or their partner drivers. It's a Cortex A9 processor, and one of the nice things that Microsoft did is when they decided they were going to join the ARM game, they went and joined the ARM architecture board, and well, they're already there because of C, but they pushed harder, and they actually helped add a lot of security to ARM. One of the things they did is that vector page that Georg talked about at FFF000, well, Microsoft sat down and said, wait, so you guys have a page that's always fixed and user read execute? That sounds like a bad idea. So the Cortex A9, for example, actually has a register where you can say, I don't want it at FFF000, I'm going to reprogram the processor to put that vector page somewhere else. So they do a lot of, they use a lot of interesting functionality on the chip to actually be more secure than in your vanilla Linux ARM kernel, for example. But nothing's perfect. One of the things that they helped ARM do is introduce a new memory management model. So there's actually an access bit on that's used on Surface. In Linux, you have to do it in software unless you're running on new architecture. They also have no execute support, so they do use a lot of things. And for reference, I just put how PTE looks like in Windows. On ARM, you get a few bits that you can use for yourself in an OS. So there's a dirty bit, there's a global bit, etc. There is one feature that ARM has, which is called privileged execute never, which is similar to SMEP on x64 if you're familiar with it. That one's not used on Surface because the chip doesn't support it. But other than that, it is pretty much just like the same thing you'd see on x86 in terms of features like no execute and randomization. So you've got a standard split on Windows, which unlike Linux, which uses 3 gigs and 1 gigs, on Windows we have 2 gigs and 2 gigs. So if you look at this picture, I'm going to make a little separator here. What's above this green line is basically going to be your 1 gig user space and your other gig of user space. If you're familiar with the Windows OS, you'll recognize this region as being the region where DLLs usually load. Microsoft DLLs always load in 0x6000 and higher, so that's all user executable pages. And then below this green line, we have, and here, this is all the heap and the stack, so non-executable memory. And you can see pretty much, I mean, I could zoom in, but pretty much all of it is non-executable as you'd expect. Down here, we have the kernel. And so we have things like the heap, the page pool, the stacks, and then the colored areas that are bright are going to be kernel code, driver code, and then the blobs that are here, these are going to be writable and executable, as will these blobs here. And of course, do the same thing and try to see, are there regions that are identical? And so what we've observed is that there is randomization in terms of what piece of data goes in each region, but the actual regions, because they're 32-bit, are quite similar. So if I can go to this slide for a second, this is one machine, this is another machine, and in the middle we have the AND of that picture. So basically putting the two pictures together and keeping only what were the same. And you can see that everything that you see there in the middle is identical across both machines. Now 2 machines isn't great for sample size, but if you took 10, 20 machines, you'd find a slightly smaller region, but there still would be regions that match. And what you're basically seeing is you're seeing non-page pool, which is the heap, or page pool, which is also the heap, be the same place. But yes, the pool is at the same place, but the contents are still randomized. So the heap allocator will pick different addresses within that blob for a new allocation. So likely you're not going to find static data, but you're going to find static regions where data can be found. And so if all you're looking for in your exploit is, I need a place to dump some code, so I don't need to do a ROP sled, but I just need to basically write somewhere where I know it's going to be writable, you can still leverage that fact. The data that's there is not going to be constant, but if you don't care about the data, just that you have a location, that's definitely useful. The other thing that was interesting is that the vector page, the one that Georg mentioned, FFFF000, is actually read and execute. Which is interesting because I just said Windows doesn't use that. Windows has a fancy other feature. So why is it there? We'll see in a second. The other thing is that IO space mappings, so things like the frame buffer, things like the registers that belong to different devices, they're actually mapped read, write, execute in many, many cases. Now in Windows 8, the security team added a flag that lets you make the IO mappings non-executable. It's kind of hacky way you have to OR in a flag in a place where you're not supposed to put in flags, but they did it that way for backward compatibility. So it's likely that some of the vendors like NVIDIA, for example, that wrote a lot of drivers for Surface didn't use that flag. And so a lot of the IO space mappings are read, write, execute. On the other hand, you're talking about device memory. So the fact that you can write into, the VGA BIOS, well, not BIOS because it's Surface, but the fact you can, overwrite EFI or overwrite something like that may not be necessarily interesting. So the other thing we saw was that in user land, everything was always random. We didn't get any picture where, of course we only had a few devices, but we didn't get any picture where there was anything similar in user mode. So in user mode, from one device to another, from one boot to another, everything was randomized. Now obviously through 1,000 devices, there would have been some mappings that are similar, but a much, much better job. In the kernel, those IO space mappings were causing an issue there. So all those places that I mentioned which are constant, so the data is not constant, but the fact that the read-write is constant are places where you could drop in a payload, and some of those areas are read-write-execute constant, and so you can always drop a payload in there. The other thing that was interesting, which is not really a security issue, but it's kind of odd, is that little dot, that blue dot, it's there in Windows too, which is weird because the vectors are supposed to be at the VBAR register. So what Microsoft does is they put the vector table in the kernel, and because they randomize the kernel, the VBAR, the virtual base, the vector base address register is always different. Yet for whatever reason, maybe some leftover code, who knows, 0xFFFF000 exists, and it is readable and executable. But there's nothing there. It's all zeros. So probably a leftover, something that actually need to check if 8.1 fixes, but it's an oddity. So you can't write to it, so it's not useful, and you can execute zeros, which don't really mean anything on ARM. Physical memory, again, we took two devices, and then in the middle we ANDed, and again what you're seeing is device memory here. So of course device memory is going to be equal, it's always going to be the same physical address on every machine, and then here's where you see the what we call the KSEC0 mapping. So the Windows bootloader always puts the boot images and its allocations very, very at the beginning of physical memory so that it can map easily to virtual memory. So there are some mappings that are always constant, but within that mapping region, which drivers got loaded where are randomized. So you know that in RAM, at that location there's going to be a driver there, but you don't necessarily know which one. In terms of user mode, again, we looked at IE, for example, and there was no obvious JIT region. There was no obvious thing that was static across one machine to another. So the other thing we did is look at the Windows 8, 64-bit. So on 64-bit, unlike that dynamic allocator, which picks a page every time for where it needs to go, when they designed a 64-bit address space, they say, well, let's just do what XP did and hard code addresses, because we have such a gigantically large address space, to 128 terabytes, that we don't really need to start allocating bits, and it's going to fragment and make it too much of a mess. So we'll just pick some large regions and make them static, but the order in which we allocate things in those regions will change. So the idea is that, yes, I know that drivers always start at FFFF something, but which drivers there will always be different. So there's these chunks of memory, and they're all about 128 gigs or 512 gigs or a terabyte, depending on what's needed what's the right space there. So I'm not going to bore you with going over this table, but basically this, you'll have the slides. This is an entire address space map of what the 64-bit kernel of Windows has. So, there's this thing called hyperspace, for example, and hyperspace is always going to be 512 gigs between these memory ranges. There's the system shared data page, which is 4 kilobytes, and it's always going to be at this address. Drivers are always going to be inside this 512 gig region. Kernel stacks, bootloader drivers. Post-bootloader drivers, IO mappings, kernel stacks, always going to be in this region. The page heap, always going to be in this region, or a little bit over it if it gets too big. Win32.sys and all the graphics system drivers, always going to be in this region. Your cache system files are all going to be in this region, and so on and so forth. Now, which file goes where, again, is supposed to be random. So these are 8 dumps of 8 different machines. And statically, it's hard to see exactly how much they change. So I've got a little slideshow just to show that it's quite varied. So I'm going to use the Windows slideshow feature. And it kind of almost looks like the game of life. So there might be the same, color to place, but what it's in that color is always going to change. And if you look at the drivers, it's hard to see with this projector, but those purple dots over there are kind of changing all the time. It's also funny to see how the randomization algorithms work. You can't see it on a projector, but there's a pixel that actually has almost an orbit. So basically orbits because it's picking random points, probably with a modulo, and each time it's going somewhere else. So fairly different, except this little dot at just at the bottom, so you won't be able to see it, which is called a HAL heap, but that's not executable, so it's not the end of the world. But we noticed by basically going over the actual data, and this is the physical dump. Again, it's very hard to see because it's a lot of pixels, but physical memory also was quite different. So what we noticed is that there were some small purple dots, so some small read, write, and execute dots that were at fixed locations. One of them, for example, was FFFF7001800. It seems random. It's in the hyperspace range. And if you pick up your handy Windows internals book, it's where the per process working set list is. Now, I'm not going to mention what the working set list is, but it's basically a memory management structure that's used by the kernel, and every process, it's written in the book, it's not a bug, always has the same address, FFF7001. But what's interesting is that for whatever reason, it's marked executable. This is just data. There's no reason why the working set list should be executable, and this is likely something that just got forgotten when they did the Windows 8 cleanup. Now, I actually looked over the data, and in some cases, on some machines, you could actually get useful ROB gadgets out of it. So it so happened that some working set list entry had just the right hexadecimal data that it corresponded to a call RDX ret instruction, or another working set list entry corresponded to, add EAX1 ret. But every machine is going to have different working set. So unless you're exploiting a process that you know how its working set is going to look like, and you're sure that your exploit is executing in the context of that machine, you're likely not going to be able to predict where a ROB gadget is going to be. There's probably going to be useful ROB gadgets somewhere, but it's going to depend on what the working set list looks like, because it's not code. It's data that could be misinterpreted as code if you get lucky. But still something that should not be executable. We also found FFFF780, 1000, 782, 80 million, and 781, which correspond to the other 3 working sets. So every process has a working set, the system cache has a working set, a page pool has a working set, the file system cache has a working set. All of these were all mapped probably with the same helper code in the kernel, and they all end up RWX. So if there's certain machines that have particular page pool semantics that cause particular page pool working set list entries, you could kind of maybe on some machines somewhat reliably think that there's a ROB gadget somewhere. But again, it's not a big deal. It's just something that should be fixed to secure the system a little bit more. We also found some less reliable observations. So there were 2 other ranges that we found were RWX, and these were in the what's called the system PTE region, which is where IO space mappings go. So we actually looked at what physical memory this corresponded to, and one of the blobs corresponded to A0000, which you might recognize as the VGA frame buffer, VGA BIOS, and VGA ROM and the BIOS ROM. So these are basically physical device mappings, and the IO space allocator doesn't have that good randomization. Plus, these APIs are called very early in boot, so there might not be a lot of entropy. And so on 8 out of 10 dumps on different machines, they always ended up at one of those 2 addresses. Now again, this is device memory, so it's not necessarily useful. There could be 16-bit code in the BIOS though, or maybe 32-bit code if you have EFI that you might be able to jump into if there's a red. So it could be useful, but again, not fully reliable because not all machines do this. So then we also looked just a few days before at Windows Blue, Windows 8.1, to see if anything had actually changed there. One of the main things that changed in Blue is actually completely re-architected what the kernel virtual address space looks like. So a bunch of the regions that were not used are now used, and the system cache is now 32 terabytes instead of 1 terabyte. Kernel stacks and system PT are now 16 terabytes. The non-page pool can be as big as 22.5 terabytes. And so a lot of things became bigger, so now obviously that means there's more entropy for kernel stacks. Now they've got a 32 terabyte region where they can drop kernel stacks, not just a 512 gigabyte region. And by moving things around, this also gave them an extra 120 gigs of page pool, so now the heap can be up to half a terabyte. Again, that gives more entropy for heap allocations. The other thing we noted when we did the physical dump, if I can go see where the other one was. So if you look at these physical dumps, the top is very, very busy. The bottom, it's almost all black. But in Windows Blue, it's a lot more distributed. So it looks like the physical memory allocator is a little bit better distributing physical allocations. So these are some architectural things we noticed. We also went, of course, and looked at the pages we had found were fixed in Windows 8. And all the working set pages are actually now map read only. So those working set lists are no longer read, write, execute on Windows 8.1. They're only read and execute. All the IO space mappings we found, they were still not randomized that well, but they were no longer execute either. So now they were just read and write. So we looked only at a few Windows 8.1 dumps, but we could not find a single static location which had RWX pages and static data that you could jump into. So for raw purposes in 8.1, you know, I'll put my reputation on Microsoft's line here and say it is the most random kernel and the most secure random address space that I've seen in any OS or that we've analyzed. There doesn't seem to be any fixed location with any code that you could reliably jump into. So kudos Microsoft. Now Alex also took a look at iOS 6 and fortunately did not really give me a lot of information about what he found. So all I'm really going to do is kind of go over a little bit of what the slides say. And basically what he found was that there is a vector page, but unlike Linux, it's execute supervisor read only. So not writable, not executable from user mode, so not very useful. Found a page FFFF1000 that is user readable, supervisor writable, available in every process, and has some performance counters, but it's not executable. So he thought maybe the perf counters could be used for a side channel attack. If you know the perf counter will increment when something happens, there could be something there, but nothing that he was able to exploit in any way. He did some KSLR, some kernel address space dumps, and noticed that they were fairly different, but they did have the issue that a lot of the stuff was, there were some regions that were read, write, execute, but not necessarily static. Physical memory dump looked identical across all 3 machines. So in terms of RAM randomization, it doesn't have the kind of algorithms that Windows does. And in terms of user mode, he found that there is a JIT region that you can identify in, for example, mobile Safari, but it is not fixed. So nothing really that, this is basically just going over different regions, but he didn't really find anything that was fixed or useful or exploitable in any way like we did on Windows or Linux. One thing he did find though is that if you jailbreak with the evasion code, it'll actually leave the kernel mappings as RWX. So you actually had to jailbreak and then undo the tomfoolery they were doing. So by jailbreaking your phone, you're actually making it more vulnerable because you're losing the protection that the MDM patch, for example, has with Android. So you are going to have writable and executable kernel pages. And as I mentioned on the picture here, all the physical pages were at the same place on all the 3 phones he used. So if you have a JTAG attack or DMA attack or something through USB, you know that you have a physical address where you can go on any iOS device. For Mountain Lion, basically user mode was pretty well randomized. And in the kernel, he basically just mapped. We didn't really have a lot of time to find anything useful. Unfortunately, Alex had some family crisis, so he kind of had to leave things here. In his initial search, he didn't really find anything that was too useful, but he did find that the EFI runtime services were left there, read, write, and execute. And the EFI runtime services, because they're allocated very early, are going to be at the same address. So, and all Macs are EFI machines, so that could potentially be a useful address. So in terms of thanks, Sean was a guy who helped Alex get the RT dumps. Alex used the jailbreak from Evasion, of course, to do his work. And the binvis tool is useful. I think you guys use it for the Hilbert curves. You want to thank anyone else?
Well, thanks for the people that work with us on responsible disclosure, even though it didn't get patched. But yeah, at least we could drop ODay that way, right? And that's probably it. Are there any questions?
Yeah, any questions?